Actually, I'll stay here. Okay, so my name is Rex. I'm going to be talking about cut points for clinical prediction models and how we could inform our selection of cut points for improving value-based care. So a brief outline of the talk. I'm going to have a background into clinical prediction models and what cut points are, how we integrate these into sort of the economic considerations into cut point selection methods, some results from a simulation study, and some results from a simulation study. So first, there's clinical prediction models, and these are sort of the system which underlies a lot of decision support systems that clinicians will use to make better healthcare decisions. There are models which are diagnostic, and these are sort of informing us of whether a patient has a condition, and there are those that are prognostic, which are predicting some future healthcare event or diagnoses. Either way, these are estimating patient risk given some data about that patient. So for example, we could be having a model that predicts inpatient falls, say in the next 24 hours from the time of prediction, given some data from that patient. And this would be a prognostic model. How do they inform the user or the clinician? So there's an option to provide the probability, the predicted probability from the model, or the odds of a fall, say, or you could give a binary classification, say yes, they will fall, or they're high risk and you should get the intervention, or no, don't, or they won't fall. Or you could have multiple categories. So ideally, we'd have this like predicted probability, as this is most informative to the user. So in this recent, well, not that recent, but in this good piece about the implementation of clinical prediction models, this middle section is a bit hidden away, so zoom in. They talk about predicted probabilities. They don't talk about high risk and low risk and using these as clinical, in the context of clinical prediction models. They talk about predicted probabilities, and they do say that they're hard to interpret. But a lot of these end up being classified. So in reality, predicted probabilities are best, but often we're dealing with predicted classes, say give the intervention or don't give the intervention. They're gonna fall or they're not gonna fall. Here we've got two examples where there's an early warning system on the bottom left, and for given scores, they're given distinct behaviors or interventions. For example, when above a certain score, there's meant to be a MET call, a medical emergency team call, and as soon as this criteria is met, there is an intervention in place. You know, they are doing the MET call and there's a cost involved and hopefully a positive patient outcome or an improvement to that patient outcome. On the right, we have a sort of prediction model for melanoma. We can see that there's a whole lot of sort of segmentation within this image on different moles on the person's back. And there's also a classification here. So there's low risk, which don't have a border. There's a sort of medium risk that has a yellow border and a high risk that has a red border. These have cut points on the predicted probabilities to assign this classification. So what are cut points? They're really a line in the sand on the beaches of predicted probabilities. So above which would classify the prediction as true, and below which would say the prediction is false, or predicting the positive event or the negative event. So these, going back here, if say for the melanoma detection model, they have sort of three classifications, say low risk, medium, and high risk, they've got two lines on their beach. So between the two lines would be medium risk, and above the highest line would be high risk. But they're still using a cut point. I'm going to focus on a binary classification model for the rest of this simulation talk. So here's sort of a simulation of what predicted probabilities may look like and what our cut point does in terms of changing our confusion matrix. So if we have a quite common outcome, we have predicted probabilities that are closer to that that prevalence. And if we have a more discriminant model, the predicted probabilities are greatest separated by the model. And this may shape where we want to put our cut point. So of the available cut point selection methods that are already out there, all of these maximize some other performance-based metric. For example, the Uden index maximizes the sensitivity plus the specificity minus one. And all of these pretty much do the same sort of mix of, sensitivity and specificity, or incorporating something from the ROC. But none of these consider anything beyond the model itself. None of them consider the costs, patient outcomes, or the interventions that are available and the decisions being made. So the objectives of this study were to integrate information of patient outcomes and treatment costs into cut point selection, evaluate how it compares to other cut point selection methods using a simulation study, and I'm going to get sidetracked a bit, so that'll be the second part. So for evaluation, we're really interested in maximizing the net monetary benefit that's provided for each possible classification using each cut point. So the net monetary benefit is a monetary term which captures both the patient outcomes as well as the healthcare costs involved with that classification. And together, we first have to find the number of events within each of the possible predictions. So true positives, false negatives, and true negatives. And we also have to find a value for the net monetary benefit assigned to each of these four categories. So I'll talk about this later on as well, but for example, a true negative has zero cost because they don't have the cost of the outcome, nor do they have the cost of the intervention. Whereas a false positive receives the intervention, but just doesn't have the outcome, so they have the cost of the treatment. A false negative didn't receive the treatment, so they have the full cost of the outcome. And a true positive, has a cost of the treatment as well as a cost of the outcome, but that's reduced by the treatment effect. So for our cost-effective cut point, we're really interested in something that maximizes net monetary benefit. And I use a R package by Christian Thiel called Cut Point R. This incorporates a lot of the existing cut point selection methods, but it also lets you pass your own metric on which to maximize or minimize. And he also responded to my Twitter DMs and helped me incorporate everything that I needed to make it all work within his framework. So we apply a custom metric within Cut Point R to maximize the net monetary benefit. And that looks a bit like this. I'm just going to talk about this separately. So this is the function that we're wanting to maximize. And this really captures the total net monetary benefit for that cut point. So we have on the top the net monetary benefit assigned to each of these four classes. And below here we have the number of samples within each of those four. So this first part of the equation is a number of true positives multiplied by the net monetary benefit assigned to the true positives. The second part is the number of false positives multiplied by the net monetary benefit assigned to the false positives, and so on and so forth. So we're maximizing the sum of the net monetary benefit for that given cut point. So for this simulation study, I'm using values. I'm thinking about an inpatient falls use case where I'm trying to prevent falls with a prediction model, or assign the use of a patient education intervention that is to prevent falls. We're using healthcare costs, effectiveness of the intervention from the literature, and quality results from falls, multiplied by a willingness to pay of $28,000. We use point estimates of these for obtaining the cost-effective threshold, but we're incorporating the uncertainty of them that we get from the literature for the evaluation process. So for the simulation loop, first we sample some training data, given the model discrimination and the event rate. We fit a prediction model, in this case just a logistic regression model. We obtain some cut points using each of the cut point methods. The cost-effective one, just using the point estimates. We sample some validation data from the same distribution. We get predicted probabilities for the validation data using the fitted model. And we get net monetary benefit values for each of the 4 classes by sampling the cost and effectiveness from their underlying distributions and combining it each time. So for each iteration, we're doing that separately. And we calculate the net monetary benefit for the validation set under each cut point method and store those results. And we do that 5,000 times. So I'm going to talk a bit more about the data sampling process that I used, because it was news to me when I did it. So existing approaches for sampling data for a prediction model would mean sampling coefficients to be used in a prediction model from a multivariate normal distribution, and then using those to sample the outcome. But in this case, there's no clear ability to me to specify the event rate or the model discrimination. I really want a function which looks a bit like this, where you can just specify the number of samples, the discrimination, and the event rate, and it gives me a data set that ticks all the boxes. So my approach was instead to transform the area under the curve into a cutpoints D, and there's a reference down the bottom that has a formula for that. Then we sample the number of positives in that sample from a binomial distribution, given the event rate. And once we've got those in this first part of the function, I can just then sample the negative events, or the single predictor from for the negative events from a normal distribution with a mean of 0 and ST of 1. And for the positive events, I sample from a normal distribution with a mean of cutpoints D and a standard deviation of 1. And then I have my data set. So it's just going to be a single predictor in this model, predicting the binary outcome Y. So the good news is when I sample these data, fit a logistic regression model, comparing that to the actual events, I get an area under the curve very similar to the model discrimination that I specified. And better yet is that this results in a calibrated model, which may not be realistic, but we'll get to that later. So for the primary analyses, for the Inpatient Falls use case, the costs and outcomes came from the literature. We're using an event rate of 3.6%, which is about right for acute care hospitals in Australia. And we're simulating with a model area under the curve of 0.7, which is about as high as the trustworthy results in the literature. Okay. And so here's actually this is the incremental net monetary benefit. So the additional net monetary benefit compared to the reference strategy of just treating all, which is sort of the common approach used in Australian hospitals. So you see that treat none is worse than treating all, which is maybe sensible. But all the cut point selection methods, including the cost-effective one, were pretty much the same in terms of the INV. Maybe a tighter distribution for the cost-effective one, but that would be about it. In the end, the cost-effective approach was the best for 40% of all 5,000 simulations, but the median NMB and the average net monetary benefit, was about the same for all the cut point methods, so not a huge win. I did some sensitivity analysis to see how it would be if the model were worse or better. And I found that when the model discrimination was worse, say it had an area under the curve of 0.55, the cost-effective approach was more better. The difference between the cost-effective approach and the other cut point methods was greater when the model discrimination was bad or worse. And when the model discrimination was better, when we had an area under the curve of 0.85, they were all pretty much the same. I guess it's very easy to discriminate positive and negative events at a certain point, and they're all going to draw a similar line in the sand. When I simulated that the events were rarer, when they happened just 0.5% of the time, the relative benefit of the cost-effective approach over other cut point selection methods was greater. So we get a bigger separation here. And oddly enough, we also get better separation when we have really common events. So this is a bit of a curly one. And I think it's down to a tightening up of the distribution of the selected cut point for our approach. It was more spread here, and I think that's why we get a sort of worse result in terms of net monetary benefit for this case. It's just a bit unfortunate for my primary analysis. So I've got a Shiny app to sort of wrap this all up. You can use simulated data or upload your own, if you like. And you can add any of those cut point methods that I've mentioned, as well as a cost-effective one, but only if you add numbers to the boxes here. After doing pretty much all of this, I then saw some work from someone else that said we've got a cost minimizing cut point. I'm like, oh, well, that's pretty much the same thing. Damn. And they work by finding this threshold based purely on the costs assigned to each of those four possible classifications. So this isn't they're not using predicted probabilities and actual events to find this cut point. They're just looking at the relative costs of the outcomes. And an assumption of this is that the prediction model is well calibrated. If the predicted probabilities aren't realistic or representative, then this won't work. So I just wanted to test that compared to our approach. So on the right here, I know it's pretty small, but this middle panel is our primary analysis, and I've added on this cost minimizing threshold on the far right. And the main takeaway is that for when the model is well calibrated, i.e. the simulated data was as I had done it, the cost-effective approach, or my approach, was very similar to the cost-minimizing approach. So pretty much the same. And that was true for all the sensitivity analyses as well. And on the right part of this, this plot is the like 500 calibration plots all overlaid. So these are well calibrated. But as soon as I introduced any sort of miscalibration in either direction, the cost minimizing approach sort of fell off a cliff while our approach sort of stayed as it was. This is on the assumption that the miscalibration is the same in the training set as it is in the validation set though. But it does handle miscalibration better. So in conclusion, considering cost when selecting a model cut point may facilitate value-based care, and optimizing the net monetary benefit in the cut point method is better than existing cost minimizing approaches, especially when the model is poorly calibrated. But the best approach may be to treat all or treat none. And I thought that was really interesting, but it would require doing the simulation sort of over and over again with different parameters to represent your context. So I thought, well, I've already made the code, I may as well wrap it up for someone else to use, or myself, who knows, and I made an R package called predict NMB. So there's a link to it on my GitHub. It's still in development, so everything's changing, so don't look too closely. And this is really focused on answering how would my model perform regarding the net monetary benefit under several cut point methods, including treat all or treat none. And what happens when the intervention changes? What happens when the model improves? And what happens when the event rate changes? And this applies to both diagnostic and prognostic models, as long as it's possible to cost the outcomes of those classifications or misclassifications. So I'm going to talk about an example here. Here we have healthcare costs, a healthcare event which costs $100, and I'm going to use a hypothetical treatment that reduces the probability of these events by a third, and that costs $10. we're going to walk through how I would do this. So we first need to create a function which returns a named vector containing the net monetary benefit assigned to the 4 classes. So here I have the false negative, the full cost of the outcome, so $100. The true negative has no cost and no treatment, so $0. The cost of the treatment, $10 for the false positives. And the true positives have the treatment cost as well as the full cost of the outcome that's moderated down based on the treatment effect. So the treatment effect reduced the events by 1/3, so we take that off the cost of the outcome. You might see every time I run this function, I'm going to get the exact same values, but this may not be representative of real life when we have uncertainty on these parameters. So what if I didn't know the true effectiveness of my intervention? I know it's about 1/3, and I might have some literature to support that. Then we could sample the effectiveness from a beta distribution, say surrounding about 1/3, and I could sample my costs, because I'm also uncertain about those, from a gamma distribution, and this might surround about $100. I now want to have a second function which incorporates this uncertainty. So I'm first going to sample the effectiveness from the beta distribution, the cost from the gamma distribution, and just define the treatment cost up top and pretend I'm really certain about that. It's just going to be $10. I can then combine that within the named vector and return that, so that every time I call this function, I'm going to get slightly different values, and that will represent a realistic simulation of when I'm not really sure what those true costs are. This is the same process that I did for the simulation study that I've already talked about, but I'm now just showing you how I would do it within the package. So there's 2 main functions within this package. There's do NMB sim. I know I'm not very inventive with my names. I haven't come up with like parsnip or mutate or something sexy like that. And this takes all the inputs for the simulation, and it just does one simulation. One set of simulations, I don't know, the number of simulations, it does 5,000 here for the one set of inputs. So we have the sample size for the validation set, the model discrimination, the event rate of the outcome, and then we have a function which returns the named vector that's used for obtaining the cost-effective cut point on the training data, and we have a second function which is used to sample from the underlying distributions and evaluate the net monetary benefit of the validation data within each iteration of the simulation. We can also pass all the cut point selection methods that we want, and we can also define our own and pass those as well. So the resulting object just has some details about what was done, but I've also got some nice methods to have a look. So the plot method makes these fun plots to look at the net monetary benefit assigned with each cut point method, and you can also provide arguments to look at the incremental net monetary benefit or the cut point selected as well. So the parent function to that would be screen simulation inputs, and this is pretty well the same, but instead of passing a single value to each of these inputs, you can pass a vector or a list of values. So for example, here I'm going to pass a whole range of values for the model discrimination and a whole range of values for the event rate. And the plot methods here will now show you how the net monetary benefit changes under each of those cut point selection methods as one of those varying inputs changes. So as our model improves, for example, our typical model where you select the cut point based on a unit index, say, is approaching being optimal. Is becoming better relative to the other strategies. Over the top, it's actually really hard to see, but this is a treat none and the cost-effective approach just totally overlapping at the top and not changing. Probably because the cost-effective approach is pretty much predicting, treat none, a cut point of 1 or so. We can also pass, ask the plot method to return the incremental net monetary benefit, so relative to the reference strategy of treat all here. And we can also select that we want to show the event rate on the x-axis rather than the model discrimination and see how that changes. Maybe pretty safe to assume, but as the falls increase in prevalence, the net monetary benefit for all these approaches is going to get worse. What happens if we have a better intervention? So say our old treatment effect was around a third, and our new treatment effect is about 40%. We would need to first define two functions. Well, we've already had this one. This is our old treatment, and this is our new one. The new one samples our effectiveness from a slightly different beta distribution, which is centered around 0.4. And we're going to make it cheaper as well. So, I mean, we think this new treatment is pretty good without having a good look at the simulation just yet. So we then pass these functions as a named list to the evaluation argument. And here I'm just going to use the all, none, and Uden cut points to have a fair look at it without a busy graph. A couple other little things here is we can pass a cluster to make it run a lot faster. So I was getting a bit lazy and impatient, so I made it run parallel. So on the left, we can see our new treatment, which is more effective, and on our right, we see our old treatment. When we're not giving the treatment to anyone, there's no change. Maybe unsurprising. As we're treating all, and it's a really effective treatment, the treat all strategy improves quite a lot, and the Uden index improves a bit. But still, is not better than treating none. So we'd still say, even our new treatment, not good, not great. There's another method that I've made to summarize the same thing in numbers. So we can make a summary table which just does the same aggregations as I've sort of shown you before. You can also pass in whatever aggregation functions you'd like to run that. And the same thing for the screen object, but this is really hectic. So in conclusion for this package, it's really interested in how good does my model need to be able to be useful in the context of how it'll be used. What is the relative merit of X improvement in my model's performance in monetary terms? And how might the viability of my model change in a new patient population or where the event rate changes? What's next? Please tell me. Please tell me what you think would be more useful in this package, or how it would be more available or accessible for you to use in your research. So please let me know. I'd like to thank my team, which is Robin, Susanna, and Steve. There's a link to the Shiny app, the package, and my slides there. Thank you.